Welcome to The Explainer. Today, we're diving into what might be the biggest unsolved mystery in all of science, the search for a theory of quantum gravity. Okay, so here's how we're going to tackle this. First, we'll go right to the scene of the crime, the places where our laws of physics just completely break down. Then, we'll meet the two titans of physics that are in conflict. After that, we'll check out the leading theories trying to crack the case. And finally, we'll get into why this whole quest for one single unified theory really matters. So this whole mystery, it really starts at the absolute extremes of our universe. I'm talking about places where our current rule books for how reality works, they just completely fall apart. I mean, just think about it for a second. What happens at the very center of a black hole? You've got this insane amount of mass crushed down into a point that's, well, infinitely small. Or what about the first moments of the Big Bang, when the entire universe was smaller than a single atom? In these places, gravity is incredibly strong, but so are quantum effects. They're both titanic forces, and right now, our physics has no way to describe them working together. And that, right there, is the whole point of quantum gravity. The goal is to find one single, coherent theory that explains everything. A kind of universal instruction manual for reality itself, Something that works for the tiniest quantum jitters all the way up to the graceful dance of galaxies. Okay, so to really get why this is so mind-bogglingly difficult, we need to meet the two theories we're trying to smash together. And make no mistake, these are the two most successful theories in the entire history of science, period. First up, you've got Einstein's masterpiece, general relativity. This theory tells us that gravity isn't really a force in the way we usually think about it. Instead, it's a property of the universe itself. So massive things like stars and planets actually bend and warp the very fabric of space-time, and that curvature, that's what tells other objects how to move. It's an absolutely beautiful idea, and it works perfectly for describing planets, stars, and entire galaxies. And then, in the other corner, you have quantum mechanics. This is the rulebook for the super tiny world of subatomic particles. It describes the other three fundamental forces of nature with just mind-blowing precision. I mean, it explains everything from how your computer chip works to why the sun shines. It's just incredibly successful. Now, here's a key detail. In the quantum world, forces are carried by these things called messenger particles. You've probably heard of the photon, right? That's the particle that carries the electromagnetic force. So it stands to reason that a quantum theory of gravity would have one too, a hypothetical particle called the graviton. But here's the catch. Even after decades of looking, we've never ever found one. It's our first big missing clue in this whole mystery. So what's the real problem here? I mean, why can't these two amazingly successful theories just play nice together? This is where the conflict really hits you. According to general relativity, space-time is this dynamic, flexible thing, like a giant rubber sheet that can bend and curve. But quantum mechanics treats space-time as a fixed, rigid, and totally flat background. It's just a static stage where all the quantum drama happens. So, you see the problem? They describe the very fabric of reality in completely opposite ways. And what happens when you just try to ignore that and force them together? Well, the math completely breaks down. The equations start spitting out total nonsense, like infinite answers to really simple, sensible questions. It's basically a giant stop sign from nature itself, telling us, nope, you're doing it wrong, you're missing a huge piece of the puzzle here. So if just mashing them together doesn't work, what's the answer? Well, this problem has led to some of the most, mind-bending ideas in all of physics. Let's meet the top two detectives on the case, the leading theories trying to figure this all out. So here's the thing. The two leading theories approach this puzzle from completely opposite directions. First up, we've got string theory. This idea suggests that at the most fundamental level, particles aren't little points at all. Instead, they're tiny, one-dimensional, vibrating strings of energy. And here's the kicker. One specific way for a string to vibrate looks exactly like the properties of that missing particle we were talking about, the graviton. Pretty cool, right? Then you have loop quantum gravity. Now this one takes a totally different approach. Instead of changing the particles, it changes space-time itself. It proposes that space and time aren't smooth and continuous, but are actually made of tiny, indivisible chunks, like pixels on a screen. And by doing that, it cleverly avoids all those messy infinities that broke the old math. Okay, so both of these are brilliant, fascinating theories. But in science, a brilliant idea isn't enough. It has to be testable. And this, right here, is where the whole search for quantum gravity slams into a giant brick wall. See, the problem is that all these quantum gravity effects are only expected to become noticeable at an unbelievably tiny scale called the Planck length. And when I say tiny, I mean we're talking a decimal point followed by 34 zeros and then a 1. It's a scale so staggeringly small that, to put it in perspective, it makes a single atom look as big as our entire galaxy. Just let that sink in for a moment. And that's the heart of the issue. We just don't have the technology to build a machine powerful enough to see something that small. Not even close. I mean, our most powerful tool, the Large Hadron Collider, it doesn't even come within 1,000,000 miles of the energy we'd need. So we're basically like detectives trying to solve a case, but the clues are way too small for any magnifying glass we could ever build. So you might be thinking, if we can't even test these ideas, why bother? Why are thousands of the world's smartest people dedicating their entire lives to this seemingly impossible problem? Well, because the prize for solving it is everything. It's nothing less than the deepest possible understanding of reality. A theory of quantum gravity is our only hope of figuring out what really happens inside a black hole, how our universe actually began, and finally, achieving Einstein's dream of a single, beautiful theory that unites all the forces of nature into one elegant package. You know, the great physicist John Archibald Wheeler summed up general relativity perfectly. He said, "Space-time tells matter how to move. Matter tells space-time how to curve." It's this perfect, beautiful dialogue between space-time, the stage, and matter, the actors. But it leaves one giant question hanging in the air. What is the stage itself made of? Is it woven from tiny vibrating strings? Is it built out of a network of little loops? Or is it something so strange we haven't even dreamed of it yet? Answering that question, well, that's the ultimate goal. That's the holy grail. And cracking it will be the final incredible chapter in the story of physics as we know it.